I've got a few slides on Sankey diagram. So just to show out who's heard of the Sankey diagram. So this may be, maybe a third, maybe half. Okay, so that's good. So you can help me if I get it wrong. Where the energy is coming from and where it's going to. And then the thickness of the line is just showing the magnitude of that energy flow. That same information, if you put color on the diagram, you can kind of peel out even more information. So here they've got the same data. So the blue are non-renewables, green is renewable energy, and red is nuclear energy going in. And then coming out, the red lines are the useful energy, and then the grey here is the rejected energy, the wasted energy that's never used. So again, you can start to see more and more information from these energies.
Not reduced, so if this molecule is oxidizing organic carbon, meanwhile it is reduced. So the residual part that is not reduced, we can find back through titration. If we titrate and recalculate, we know how much organics were present. What we do in this test is make a proper dilution of the wastewater. We add a bacterial inoculum because we need biological material to be active in there. We incubate it under very standardized conditions, 5 days at 20 degrees. And it is, like you can see, this is a commercial setup, oxytop called. There is a stirrer here, a magnetic stirrer inside, and this is gently stirred for 5 days. Now, we have two general types of processes requiring oxygen in wastewater treatment. That is carbon oxidation and nitrogen oxidation. We'll come to that later, to this nitrogen today. But here we want to know the organics. So we care about carbon oxidation. We don't want to know about nitrification, which is the oxidation of ammonia. So we inhibit it through the addition of ATU. It's a chemical compound. We can add it in a concentration of 20, 30, 50 milligram per liter, allyl thiourea, and then the nitrification will stop. At that moment, oxygen will only be consumed for the oxidation of carbon. Part will go to new cells. So this is assimilation. We call it synthesis of cells. This does not consume oxygen. Now, this is in detail what happens over these 5 days. Here, you see log colony forming units per ml. This is the concentration of bacteria. The CUD, or let's call it the biodegradable CUD, present in the wastewater that we want to determine, it will drop almost to zero. Half burning. But we keep on burning, but now, this is a bit what happens in this first BOD phase. VSS is volatile suspended solids. So suspended means it's particulate, non-dissolved. Volatile means it's organic. We can roughly assume, if we just put it on a carbon yield, half the biomass. We apply a couple of factors on this. You end up with the fact that the BOD5 is a portion ultimate of BOD infinite. If you have the bottle, you put it there, and you just leave it, and it keeps on consuming oxygen, 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 the action, then we can assume, if it's more or less constant, of course the wastewater itself, the quantity will go up and down, and the quality, the levels of organics will go up and down.
Yeah, next to nothing. And this comes back to how you're using that information. So if you are comparing a facility to all, other activities that are going on in a city or a nation, transportation is big for everybody else. For us, it's not that big, but we need to show it still.
Yeah.
So you need to see that portion. Okay, not so important for you. These are of waste that have been treated or water that have been recovered. One I kind of quickly add to this is I presented this in Singapore, and actually the MBR numbers are way to the right. They're very energy inefficient biological nutrient removal plants because we're using energy for nitrification. It just so happens the limits that we chose and the wastewater characteristics we chose, many haven't had a lot of carbon, so we're really shifting the way. We were not able to get anywhere near being energy neutral with our waste. So for task 2, I won't sweat this too much, except that we went in and we did 2 parts. One was to do a survey of utilities, and the other one is we tried to take best practices and innovations in one or two that were getting close to being near to energy self-sufficient. There was one was Sheboygan and the other one I can't.
Your variability. Part of it, what are your thoughts about eventually us getting away from using this very American thing, North American thing of energy consumption per volume of water treated? And we have such variable influent wastewaters, the ones on the East Coast versus the one in California. Easily POD concentration will be double, one versus the other.
Right.
Yet we still are,
Yeah.
we recognize it, we say it, and still perpetuate us, but by putting figures like that. And it just masks the fact that we don't know if it's really that variable.
So what metric would you use?
He came out with it.
Which is based on population equivalent, if you think about it, because
Sort of. Yeah.
it will have an equivalent oxygen demand per gram of.
So what they did is they included nitrogen and.
Oh, you put it all in one pot.
It's consent.
It was
Theoretically, it's very energy efficient, right? Yeah. So we did some that were basic nutrient removal, some that were enhanced nutrient removal, where we assumed so we need some microspore concepts to get us there. Task 3, I won't go too much detail on this because it's not really the focus today. We did do a CHP digestion and line application was the most sustainable option at the moment. And then there's also an aspect of communication. So it was all kind of to the bottom line. And they actually spent, in the report, they spent quite a lot of time going through how you decide what are the criteria that you want to use. And certain, in particular, WRF, in a research organization, there was one criteria that they wanted under the economics, which was how well established was the technology. So all the utilities, they wanted well-established technology, whereas WRF said, no, we don't want that criteria. So they actually did the TBL two ways, one with, one without that criteria in it. Because as a research organization, you don't care if it's established or not yet. We want to see what's the best, most promising approach. Whereas if you're a utility, you don't want to do the latest and greatest that's not proven. Sorry, in the report they've got the details.
A normal utility.
Normal utility. So these are overall conclusions. A lot of this is common sense, but it was nice to kind of go through the exercise and understand these different aspects. So we need a good framework within an organization that wants to be energy neutral in order to make it work. That means you need to have champions within that organization that will drive things, otherwise things won't happen and you won't get anywhere near energy neutrality. In terms of best practices for energy use, the one that kind of jumped out massively was the need to maintain your fine bubble diffusers if you have them. So that design point, if you get the most efficient energy motor or generator and you operate it at 6.
In Europe, typically we're behind 10 and 20, but in different climates you can clearly a lot of parameters, but we can simplify it in this formula, which says the transfer rate, the oxygen transfer rate, equals the value KLA, and that is a lumped value. So there are many mechanisms behind. All of this is put in this KLA. We call it the oxygen transfer coefficient expressed per time. So all of this depends a bit on the temperature, like the diffusion coefficient, on the depth of the aeration, average time that the interface exists, on the size of the bubble, so the surface of the gas-liquid interface. Clearly, the smaller the bubbles, the better transfer you get. So we simplify into this formula, and then you can see for a given system, ideally, of course, you have a high KLA, a high oxygen transfer coefficient, and then you have the saturated concentration of oxygen in the water and the actual one. So this is your driving force. The higher this difference, the faster you can transfer oxygen. So if you're working at very low oxygen levels, you have a big transfer and is more energy efficient. Clearly, you need to be above certain oxygen levels also to get good rates in terms of the monokinetics, in terms of substrate removal, and to prevent, depends on the case, to prevent anoxic zones, anaerobic zones, if that would be not good for your process at that stage. And actually, this brings me to the end of this very fundamental, quick introduction on organic carbon, biological organic carbon removal. Maybe we can take a second to take some questions while
aspect to address for these kind of software. These are dynamic simulators. So far, I'm only showing the steady state simulations. But after break, I'm going to show some dynamic simulations, and then you can really use this where you cannot use the design softwares for calculation peak demand, looking at effects of storm events on your clarifiers and so on, which gives you more detail in the design of the plants.
So that's after 2008. That's how it looks like when they collect it, but they don't treat it in the plants. So a private collection company gets the substrate, the food residuals, and pre-treat it using a hammer mill, and that's how this co-substrate looks like when it comes to the plant. So it's of course in higher solids concentration, and it's high energy content. But still, it causes troubles. There are lots of troublemakers in this substrate. Here you see it reduces the lifetime of the pumps. All the metal pieces, they're still in there, and they're supposed to be taken out by magnetic separators and by the mill. You still see it in, for example, it pours down the pump stagers.
Time for questions and answers, and time for plenary discussion. We very much want to hear from all the participants here in the audience, particularly since this work of developing the sanitation safety plan concept by WHO and its partners is still very much a work in progress. So what we will present to you here today, we very much want to hear your perspectives, your criticisms, constructive criticisms, your comments and your advice, how to refine this concept and how to make it practical.
Ladies and gentlemen, it's a big pleasure being here. Thanks to WHO for inviting me. I don't know if the sound is good. I hear a lot of echo. Maybe you can reduce this a bit. Thank you. Maybe like this it's better. I would like to set a little bit the frame for this workshop and to speak about wastewater use globally and the challenges, and then how actually these 2006 guidelines of WHO were developed, what were the reasons. That's important to understand their strengths, but also their weaknesses, which also brings us here to this workshop, that we want to focus at the end more on the sanitation safety plans than on the guidelines per se. Now let's see if this technique works. This should move forward. This is the down one. Excellent. Thank you very much. Wastewater irrigation is very common, and it has different phases, and we see it in and around 4 or 5 cities in the world. And the estimates say that there are at least 6 to 20 million hectares globally under wastewater irrigation. I can say for sure the 6 are correct. The 6, we have the data. For the 20, there are some publications, but there are some big data anyway are around. I can't put my hand in the fire for all of them. The estimates are also that this wastewater irrigation is contributing up to 10% of what's consumed globally. And you will see in which countries this is mostly taking place. So when we look at the reuse of wastewater, there's a site we like, there's a site we love, that is where treated wastewater is used. And there are many countries where this is taking place, and the driver normally is water scarcity. So that is planned reuse, the health risk can be managed, and to make this happen and to help those countries, assist them in doing it in a safe way, the WHO published in 1989 a set of guidelines, and these guidelines are till now very well known and a lot cited, especially just one table that makes these guidelines very attractive, because it goes down to one table which everyone knows who works in the sector, and they're just very simple numbers. So if you want to irrigate anything which is likely to be eaten raw, then please take care that the fecal coli found in 100 milliliter are less than 1,000 calories. Now the upper part here, there you see there's much more going on. Sanitation has problems. So farmers were looking for safe water, have very big challenges. Maybe the upper bar there of China continues. I could show the same slide now 18 times. Because it just goes on and goes on and goes on. So there's a lot, really nothing works. That's why the streams are very polluted. So when you can find all these treatment plants, they're like white. The blue line shows how much wastewater is collected. So it goes from nearly nothing to 100%. So there's a trend in this direction. Did you see this red bar?
We know that the wastewater also has all the nutrients that these bugs can use as a substrates and grow, and which is basically the key major foundation of the treatment process. So the nutrients are there, the proper bugs are there, you get a proper treatment. Now, just like us, some of us are vegetarian, some are non-vegetarian. The microbes have the same category as well. Some have carbon source, they could take it from inorganic type, organic type, and they're categorized accordingly as vegetarian and non-vegetarian. Now here we call them as autotrophs or heterotrophs. Autotrophs are like self-feeders, like you have plants and algae, they could use sunlight and make their own food. And similarly, with the use of energy, they could use energy from sunlight or chemical, then they are called as phototrophs or chemotrophs. So there are different types of microorganisms, and not all of them that we are able to culture and see them, because wastewater comes as a dirty water into your treatment plant. But it has all the microbes in there. They could function with the substrate which is already in the system, and with use of a sunlight or any other inorganic energy source, they could bring about the water reclamation.
See, we are studying. And when it will be implemented, what is the cost effectiveness in implementing city safety sanitation plan in Devanadi?
So that's the big question. And we're talking about public health. The major objective of SSP is public health protection. So at the moment we don't have data on that. But we are convinced that a risk-based approach is going to be much more effective than just using infrastructure investment approaches. I don't know whether, Pei, did you want to add anything to
the food or the irrigated wastewater, irrigated food like a fish or vegetable. And another transmission route is a vector, like through mosquito. You can see that a lot. It's a tool to prevent the health risk for the farmer or the people engaging in the wastewater irrigated use in agriculture and aquaculture by multiple barriers. However, I can say that what the safety plan is like between the water supplier, while the SSP is more like and involve a lot of many stakeholders in this sector, sanitation sector, from the discharge point until the end of the product. One of the is the wastewater use in agriculture in the peri-urban area of Hanoi. The other one is
during the times of peak loads. So there are a number of ways of doing only.
Perhaps one of the main reasons. There are some disadvantages of methanol, including lower kinetics, but we found in New York City that we had to shut down methanol operations because of safety, and we have since gone to glycerol. There are compounds, there are waste streams containing glycerol. As the biodiesel market accelerates, a lot of biodiesel waste has glycerol and trace of methanol as well. So that is something that has been tested. It's fairly widely applied. In some cases, what I would also recommend is also consider fermentation of not some of these streams that I showed you.
I'm Mamata. I'm an environmental engineer working in Town Municipal Council, Devanagari, Bangalore. I'm presenting case study on application of sanitation safety plan in India. This sanitation safety plan trial is done in Devanagari town. Agencies involved in this trial are Town Municipal Council, Devanagari, Kathmandu Urban Water Supply and Drainage Board, St. John's Medical College, and Bioenvironmental Trust. Devanagari is a town in Karnataka in India. Groundwater. The groundwater table is 800,200 feet deep of Devanagari SSP trial. Directorate, Town Municipal Council works under Directorate of Municipal. Septic tanks will be collected from honeysuckle, and the honeysuckle will transport these waste to the dumping site, where farmers will use these waste as compost. Wastewater flowing in stormwater drains will be tapped by the farmers from drains. Will use wastewater for irrigation. The final product of this agriculture is agricultural produces, which finally goes to the market.
And we see a lot of nitrate. 29 milligrams of nitrate. For phosphorus, there was something like 7, if I remember correctly, 7 milligrams in the influent. And then what's coming out here is 4.1. So I guess the 3 milligrams that you mentioned, Krishna, is about right in this case. Or we made a model such that it will be right to what Krishna says. And then let's see MLSS and VSS. See, we ended up with something like 2,300 milligrams of MLSS, the VSS of 1,700. And then in this table, we see, make it a little bigger here. We see, these are prepared tables. So we see our COD, which is of course really high in the reactors because you have sludge in there. You measure total COD. So it's not an important number, but effluent is 35 with COD. TSS is 10 because of the simple model. VSS 7.6 in the effluent. And then there is that zero DO that I think Karthik explained in the influent, and 2 milligrams of DO in all the reactors, the diffusers, because there is a high oxygen uptake rate. You see that here it's 73 milligrams per milligrams of oxygen per.
Foodborne trematodes. 10% of world population are in culture. There are several excreta-related pathogens.
Sanitation safety plan that we are trying to use it. Actually, I have experience of using water safety plan. This safety plan can be executed, can be worked out with even a small, negligible amount of money. What experience I have with the water supply system, with a negligible amount, just with the awareness, just with the developing the community, making some sort of the advocacy. Similarly, the sanitation is also like that. We can invest a lot of money to have a sanitation plan, to implement it. Even with the smaller money, we can do some things. So it is not very difficult. What we have seen, that can be implemented. And we are doing in some way, but we have to enter into this field in a planned way, and that will give some results. Actually, I have executed many plans, like ecological sanitation I have seen, where we separate the urine and excreta, and we use the excreta as a fertilizer in many places, and the urine as well as a fertilizer. We have very good, very handsome amount of fertilizer hidden in these things. Even I would like to, the word is used for the waste. I don't like to use this word waste for the waste because it is something that can be used. It is not waste. And even the resources that we have found out in this, the waste, so-called waste, that is, actually we don't have some sort of the instrument to find out the hidden nutrient things of this excreta and urine. Actually, I have with the permission of our moderator, I would like to show some slides. That one cancer patient just treated 2 months ago and 3 times operated. And he was one of the poor family member. His liver in the Tarai area of Sunlight districts. And he was suffering, and 2 times the operation failed, and 3rd time he was asked to have another operation. And another operation, he didn't have money, and he was given a breathing pipe to take the breath and feeding pipe to have the foods. He threw away the pipes, feeding pipes and other things, and started starving. One of the trainees who got the training with me started using the urine on him and see the result within 3 weeks. What happened?
Come from for this to happen, they come from electron carriers such as NAD. So it's really critical to cell function that these electron carriers are recycled appropriately. Now, cells don't always have a terminal electron acceptor to regenerate their electron carriers and to make ATP. When that's the case, then we call it substrate level phosphorylation. Remember, it's those phosphate bonds that have all the energy in the case of ATP, right? So we can produce ATP without the electron transport chain, but it's not as efficient. But it's more common in our anaerobic processes. And again, it's good. We want that less efficient so we have less production of biomass. And fermentation is one case of substrate level phosphorylation. Again, going back to our questions of what a cell needs, we can think about the carbon source, the electron donor, the electron acceptor, how it's making its ATP. Is it the electron transport chain or is it substrate level phosphorylation? And how is it regenerating these electron carriers? So again, in anaerobic digestion, our critical processes are the hydrolysis, because we have these large molecules to break up. Once they're broken up, fermentation, methanogenesis, and then we have 2 different kinds of methanogenesis. We have hydrogenotrophic and we have acetoclastic. So what I'll do is I'll go through each of these in some detail.